Good afternoon,
Good
sir.
afternoon,
Good
sir.
afternoon,
Good
sir.
afternoon, sir.
Good afternoon.
Is my screen visible to all of you?
Yes, sir.
Yes, sir.
Okay. Let us wait for 1 more minute uh, so that others can also join. Roll number 26. Yes, mute your mic. Okay, fine. This is a new section, this is a new unit, and I want that everybody should be present so that जो शुरू में बेसिक्स हम करें तो वो सभी को समझ आ जाए so that you can understand higher concepts of this part of physics. We have completed fiber optics. I will upload assignments on Google Classroom, and I will give you time of 2 to 3 days to do that assignment. Probably by today uh, evening, I will post it on Google Classroom. Definitely by tomorrow, I will do it. अगर आज नहीं कर पाया तो by tomorrow I will load it. This will also be helpful for you to prepare for your final exam. So I think we should start. My presentation is visible.
Yes, sir.
Yes, sir.
Okay, as yesterday I said that uh, to uh, to do this electricity and magnetism unit, we require some basics of mathematics, vector calculus. So we'll do that in a short because this is not our focus to do this because we are doing electromagnetism. Let me give you a little introduction about electromagnetism. It is a new branch of physics. It is originated from electricity and magnetism. Initially, they were independent branches of physics. Electricity was studied separately, and magnetism was also studied separately. Then these branches were unified. Unification become possible because it came from the idea that electricity or varying electric field can produce magnetic field, and varying magnetic field can produce electric field. So they are connected. Electric and magnetic fields, they have some relation. So this resulted in unification, and now this is unified, uh, and this is called electromagnetism. In this, we deal with electric and magnetic fields. And before going into details of anything, let us understand basic definition of uh, uh, any field, not particularly electric field or magnetic field or gravitational field, potential field or temperature field. We need to understand what we mean by a field. Whenever it is said that electric field is produced or electric field is there in some region, or magnetic field is there. So what we mean by that in general, what we mean by electric field and what we mean by magnetic field. Electric field E is represented like this. It is electric field E is given as E as function of x, y, z, and some value or whatever it is. This is what this is representation for electric field. Similarly, we write magnetic field. It is a vector quantity, so we write it like this. So this is my magnetic field, and so on. We have gravitational field, we have temperature field, we have many such fields. So if I ask you a very simple question, uh, can you define what is a field? I'm interested only in this thing. What is a field? Forget about electric. It is electric field. I'm not interested in what I mean by electric, but I am interested in what is the meaning of second word, that is field. Any one of you, what do you mean, or what do you think field is?
Sir, field is a space where the effects of a particular thing can be observed.
Okay. Now, what do you mean by particular thing here? Effect of a particular thing. This is, you are using vague words. So particular thing, you should define what we should have a definite, or we should define it clearly what we mean by particular thing. Anyone else?
Sir,
Would you-
charge particle.
Yes. Uh, I'm saying field. I'm not saying electric field. I'm not saying magnetic field. I'm not asking you what is gravitational field. Neither I'm asking you what is temperature field or potential field. Keeping everything aside, I'm just interested in knowing what we mean by a field.
area.
Sir, a fixed area.
Mhm. It is
Sir, any area?
any area is field. Range of space. Any more ideas?
Sir, effective area.
If I put it like this, it is a space within which a physical quantity or any physical quantity is well defined and is unique at every point in this space. So by physical quantity here, we mean if we are interested in electric field, then I know that it is what it is. This is the physical quantity I'll be measuring to know how much is the electric field in at that particular point. It is F divided by Q naught, because we know field by field what you mean. When we have electric field, we mean how much force is experienced by a unit positive charge. That is magnitude of that electric field. Okay, so we should define with this what we are measuring. What we are measuring, we are measuring any physical quantity. It depends on we are talking about what field. If we are talking about electric field, then physical quantity involved to measure this field is F divided by Q naught. If we are interested in gravitational field, then I say force per unit mass is the physical quantity which we will be measuring. And this is what the physical quantity we are measuring is function of space coordinates. It is function of position. It varies with position. At different points in this field, I have different F divided by Q naught. So in simple words, I can say field is a region, it is a space within which any physical quantity or physical quantity, a physical quantity is well defined and is function of space coordinates. I think under this definition, we can include all the fields we have come across till date. Now you can, in light of this, you can talk about gravitational field. So gravitational field in some region we can define if we know the physical quantity related with this field is what we measure to measure gravitational field. It is related to F divided by m, and this F divided by m or gravitational field is different at different points in the space or different positions of the space. We can also, with these fields, let us introduce some new fields. We can say that temperature is well defined at every point in the given room. I can find temperature at this point. I can find temperature at some other point. And so as I move from one position to the other position, I see change in temperature. Even if it does not change, it is well defined. Temperature is well defined at every point of this space. So I should put this under the category of field. So I say that temperature field, and this is how it is different from these two fields, because temperature is a scalar quantity. So I say that it is what it is, a scalar field. It is not a vector field. Okay, and whereas electric and magnetic fields, these are vector fields. Gravitational field is also a vector field. So you can see the physical quantity you are measuring. If it is a vector quantity, then field related to that physical quantity is called vector field. And the physical quantity we are measuring is a scalar, then field related to that is what it is, scalar field. One more example of scalar field if I give you, and बहुत सारे examples आप अपने आप सोच सकते हैं. This is example is electric potential. We all know electric potential is what? It is work done per unit charge. So it is a scalar quantity, and you write V as, if you remember, you can write V as this. It is function of x, y, z. It is measurable physical quantity. It is, I said that this is the physical quantity we'll be measuring to know what is potential. So this physical quantity is well defined at every point in the space and has unique value at every point of the space. So that region in which W divided by Q naught is well defined is field of W divided by Q naught, or you can say it is field of electric potential. So with this introduction, let me go into the mathematical part. Why we need this mathematics to be introduced here, and how this mathematics will help us in understanding these fields in a better way. So we need to operate on these fields with some operations. Operations means I have a field. I want to know how fast it changes when we move from one point of the position of the space to the other point of the space. How these fields they get added up, or you can talk, or how this field is diverging out of any given point, how it is converging at any point. Is there any circulation in the field? So these questions can be answered if we have understanding of some basic mathematics, which is differential calculus. So let me give you idea about operator first. It is शायद पहले भी हमने discuss किया. We know that d by dx, it has no physical significance, but it is what it is, mathematical operator, and we operate with this operator. When we operate with this operator on any function, of x, it will give you what? It will give you change in that function with x, with respect to x. Okay, the best example or the best which you are aware of is position. We know position of any moving particle is function of time. And when you operate on this function of time with this operator, that is d by dt, then you find you get what you get, or you can write what is change in this function with time, which is called velocity. So just to introduce you that we have this operator, and here we have d by dx operator. This d by dx operator is not enough to operate on these fields, to find change in these fields. I'm interested in knowing how electric field it changes when we move from position A to position B. So if I operate on my field vector by this operator, that is d by dx, it can give me only one change due to, or change along one direction, and that direction is what it is, x. So I need more operators. I need to know how electric field changes due to y, and how it changes due to change in z direction, or when we move along z direction. Okay, so for that, we define a new operator here, which is called vector differential operator. This new operator is a vector differential operator, and this includes all the three components, or a change with respect to all the three coordinates, that is x, y, as well as z. So I can write that differential operator here. Let me write it. It is del operator. This is vector differential operator. In a minute, I'll tell you what we mean by vector differential operator. This gives you change with respect to x. This includes change with respect to y, and also change with respect to z. This is sum of all these partial derivatives, and this is I cap times change with respect to x, j cap times this curly over curly y, and k cap times this. This is my new operator, which I call del operator. This is del operator. Okay, and it is a vector differential operator. Okay, when I operate with this operator on any field, that is scalar field, I can operate with this on vector field. So I can find what? I can find some change in the field. I can study behavior of my field. How field is behaving. What is the nature of field? Okay, if particle is moving, we say that by operating on position of that particle, if I operate with the d by d operator, I find velocity. If I again operate on velocity by d operator, you find acceleration. So we know how particle is moving. In the same way, but to know more about these fields, how they are changing, how they are diverging, how they are there is rotation or circulation in these fields, I need to operate on these operators, on these fields by this operator, that is del operator, to have more understanding about these fields. So this is the introduction why we need mathematics here, and why we are doing this electricity and magnetism unit. So we have operators like d by dx operator. We have operators like d by d square over dx square operator. This is double derivative if I differentiate on any function 2 times with respect to x. So you know this. And this is journal exam. This is what this is my differential equation. You understand this differential equation. You have seen this. This is second order differential equation, and I can write this as operation of this operator. You can see I have taken y out, and this is equivalent to, this is what this is like, operation of this operator. Now I have introduced one more operator. This is simplest operator. This is second order, okay, derivative, and this is what this is, another operator, d square over dx square plus a d by dx plus b. If I operate with this operator on y, or symbolically you can write that operation of operator L, which is this, on y equals to 0. So I can write this differential equation. So just to give you idea what I mean by operator. Okay, need not to worry if you need not to go into much details of this. Then I introduced to you del operator. It is this operator. Okay, this is vector differential operator, and this is three-dimensional vector differential operator. Okay, इसका components, तीनों components you can write. Del x is what it is, I cap, curly over curly x. This is only x component of del operator. This is having another component, that is y component, and z component. So this is what this is, differential operator. Like all other operators, it has no physical meaning, no physical significance, but it makes sense when we operate with this operator on any function. Then that becomes meaningful, or that physical quantity will be having physical significance. When I operate with del operator on on say temperature, scalar field, temperature is scalar field, then I get gradient of scalar field. So that uska significance hai, that has significance. Okay, or like position, where it is what it is, d by dt itself is nothing, but when I operate with by this d by dt on position, then I get meaningful physical quantity, which is velocity. Okay, so operations, or I have introduced what are scalar and what are vector fields, how they are general notation, or how we denote them. It is phi is generally used for scalar fields, and it is function of x, y, z. E is a vector field here, and A is generally used for vector fields, and it is written, vector field is written like this, and scalar field is written like this. Okay, so now operation is important. ठीक है, इस मैथमेटिक्स में अभी हमने कुछ भी नहीं किया. I have simply introduced to you a differential operator, del operator. And why we have introduced this del operator? Because when we will be operating with this del operator on our fields, we can explore them more, or we can understand our fields more. So let us now study, or let us try to understand how we operate. What is this now comes mathematics, how we operate with this operator, differential operator, on scalar fields and on vector fields. So there are three different type of operations of del operator. On it is now vector operator. It is not simple d by d operator or d by dx operator. In that case, we said whatever is your field, it is scalar, vector, d by dt or d by dx, you can operate simply on anything. But here we have different ways of operations of del operator. Okay, so I have del operator. I can operate with this vector operator on scalar field. This is my scalar field, and this operation is what it is, operation of vector field, sorry, operation of vector operator, differential operator on scalar field, and this is called gradient of a scalar field. I'm writing in short gradient of scalar field. I'll give you example of this. This is gradient of scalar field, and interesting is if I write it in mathematical form, then you know that del operator is what it is, I cap partial derivative with respect to x plus another component of del operator, that is derivative with respect to y, plus k cap and derivative with respect to z. Operation of this on on scalar field, on scalar field. This is simply what? This is operation of curly over curly x on this, that is scalar field, then operation of this on scalar field and operation. So I can expand, I can write how we operate with this operator, or how we do this operation. This is I cap curly over curly x partial derivative of scalar field with respect to x, plus it is j cap partial derivative of scalar with respect to y, and k cap partial derivative of scalar field with respect to z. Now you see what you get. You get these three components of gradient of phi, or gradient of scalar field. This is component having direction I cap. This is j cap and this is k cap. These are vector components. These are vector quantities. So this is a vector. Resultant is a vector. When I operate with this operator on a scalar field, what I get a vector field. And what is significance of this? What it is doing? It is finding, or let me say it is a vector field, so it should have direction, gradient grad of gradient of psi scalar is a vector quantity. As it is a vector quantity, it will be having both magnitude as well as direction. So we can see what is magnitude of this gradient of psi and direction of this gradient of psi. Wait for a minute, but excuse me. Okay. So gradient of scalar is a vector quantity. It is a vector field. And if it is a vector field, so we should know what is magnitude of this vector field and what is direction of this vector field. So direction of this vector field is perpendicular to the plane on which scalar field is constant. and this is the direction in which change in this field is maximum. Okay, magnitude you can find. You see what is magnitude of this vector. It is square of all the components and under root of that. So you can write that as well. So let me give you one example of operation of this type of operation. You have seen in your +2 level, you say that electric field in x direction is negative of gradient of electric potential. This is what you have done. This is nothing. This is what we have done, what I'm writing. You have done this in one dimensional direction or in one direction. So we have written it in terms of what we have replaced this d by dx operator by del operator because it is three-dimensional counterpart of d by dx. Okay, and what about direction? If I say my electric field is what it is a uniform electric field here. And which is represented by what? Which is represented by equipotential surfaces. These are what? These are equipotential surfaces. And at equal distances, if we place these equipotential surfaces, that means what type of field it is? It is uniform electric field. And this is what? This is that uniform electric field. So you can relate it to what we have discussed, E, or you can find gradient of this. That means if I move along this direction, this you can say is X direction. This is EX. So how this changes per unit distance, that is potential, that gives you strength of electric field. If these equipotential surfaces are close enough or they are close to each other, that means d by dx of
अभी
E.
चाहिए मेरे को, अभी ऐसे वापस थके जैसे लग रहा है.
Who is this? Who is this? Check your mic, beta. Be on mute mode. You are disturbing others as well. So this is, and direction is what? And direction is perpendicular. Direction of this field, which is gradient of V, is perpendicular to the surface on which V is constant. Perpendicular to equipotential surface, you can say. Okay, so this is the best example which you have done earlier also. This is one type of operation. This is gradient of, you can say, temperature field. Temperature itself is a scalar quantity, whereas gradient of temperature field is a vector quantity. So gradient of any scalar is a vector. It has magnitude and direction. You can find magnitude. You can write direction. Direction is perpendicular to the plane on which scalar is constant. Has three components, as it is a vector quantity. Now it will be having three components, and those three components are, you can see these are the three components of gradient of any scalar field. And it points in the direction, जो आपका gradient of scalar होगा, that is perpendicular to the plane on which V is constant, and that direction is what? It is the direction of maximum change in the scalar. Along this direction, you can see there is no change. Along this plane, there is no change in V because it is equipotential surface. And in this direction, change in V is what? It is maximum, and that is the direction of gradient of V. Okay, and as I said that operation हम पहले ही देख चुके हैं. There is one small problem for you. You can find gradient of magnitude of position vector. If I have, let me say that this is any xy plane, or you can even xy, and you can even say it is a space. And this is what? This is position vector of any point P having coordinates x, y, z. So I can write position vector R as three components of R as xi cap, plus y j cap plus z k cap. But magnitude of this position vector is a scalar quantity. Magnitude is only what it is, x square plus y square plus z square whole under root. This is magnitude of r. Okay, and gradient of this magnitude of r. Gradient of r I can find. And you can analyze what we have discussed, what this gradient of r is, what is direction of this gradient of r, and what is magnitude of this gradient of r. Okay, this is exercise for you. You try this and then we'll discuss it in more detail. Okay, if gradient of any scalar, it is 0 at some point x, y, z. Okay, so that means what? Either you have reached maxima or minima. If I plot this with respect to x, y, z, this scalar field, then gradient of this scalar field 0 will be at either maxima or minima. Okay, you know this is like what, this is slope. Okay, so you find gradient is nothing, it is slope. So gradient at maxima is 0 and gradient at this gradient is 0. This is gradient, this is positive gradient, this is negative gradient. Similar is true if you reach minima, this is what, this is minima. Then again you see that gradient is what it is, 0. Okay, so we are not going into much mathematical description, so we need to understand physically what this all means. Then we have another operation of, we are dealing with del operator, and we have another operation of this del operator, and that operation is on vector field, and this operation is divergence of a vector field. Okay, so divergence of a vector field, mathematically, if you want to see divergence of the vector field, it is, let me write del operator. This is three-dimensional vector differential operator. Let us operate with this operator on vector field, and if I have a vector field, it will be having three components. That is x component of vector field plus j cap y component of this vector field plus z component of electric field. So operation, this is what this is. This is dot product of these two vectors. This is vector. This is also vector. So you get what I dot I is. I dot I is 1, and I dot j and I dot k, these are same, and all other perpendicular vectors, unit vectors ka dot product is 0. So I can write what I expect is, I expect only this to be non-zero, this product to be non-zero, and this to be non-zero. So I can write, it becomes what? It becomes d by dx. I have replaced, if you see, I have replaced partial derivative by total derivative now. Why with total derivative? Because this is operating on ax. So it is only x component. बेटा किसी का unmute है mic. Then we have d by dy of ay plus derivative with respect to z of z component of this. And this is a scalar quantity. You can see that this is what? This is a scalar quantity. It does not involve I cap, j cap, k cap now. So divergence, mathematically, this is how we find divergence of any vector field. And as it is a scalar, we need not to worry about direction of this divergence, but we need to know magnitude of this divergence, which is there, no need to worry. And with this, we need to worry about physical meaning of divergence of any vector field. It is nothing. Divergence is what it is. It is outflow, या फिर it is outward flux, or it is flux. So outward flow of any electric field is measured by taking divergence of that field. So we can see different type of fields, and we can predict by looking at those fields. We can predict what should be divergence, whether there is some outflow in that field or there is no outflow in the field. Okay, so this is mathematically how we do it, the mathematical operation. It is a scalar quantity. Geometrical interpretation means how much vector field spreads out or it diverges from a point. जहाँ पे हम divergence निकालना चाह रहे हैं, I'm interested in finding divergence at any point. So we see from that point how electric field is flowing out or spreading out. Okay, divergence is 0 if nothing is spreading out, or we'll see if it is, and it is positive if there is spread of electric field, outward spread of electric field from that point. And if there is inward convergence of field at this point, then divergence, that there is negative divergence. You can say that it is convergence. And in case divergence balances convergence, so then this is what it is, 0. Divergence is 0. Okay, so we can say that we have example for positive divergence. If I have a positive charge, so I know electric field is what it is. It diverges out, or it is represented by these lines, electric lines. So you can see this is representing electric field. These lines are representing electric field, and electric field is diverging out here. So divergence of electric field here is positive. This is positive. Positive means it is diverging from the given point. This is showing divergence. Not only this is divergence, and it is better way. It is in better way. It is represented like what? This is smaller vector here, and then as I'm moving, so this is how it is diverging out. And you can see then one more type of divergence you can see here. This is field, and you can see that divergence is there. If I put some volume here, so जो इसके अंदर आ रहा है, that is lesser, है ना? Inward or convergence is lesser than the outflow. So divergence, so net divergence we can find here. Then as I said, that negative divergence or convergence, if I have a negative charge here, electric field will converge. Okay, and then that is what that is. Divergence of that field is what it is, negative. Divergence of negative field due to negative charge is what it is, negative. And 0 divergence, you can see that whatever is flowing in, ठीक है, वो outflow भी हो रहा है. तो convergence and divergence, यहाँ इस point पे you can see this field is flowing in and this field is flowing out, and they are equal fields or uniform same fields. So you can see that divergence is balanced by convergence. So when we say that this is 0, and that is what that is, flux is 0. Okay. For example, I have what you know that Gauss law, जहाँ हम कहते हैं कि positive charge होगा enclosed, so then we find that closed line integral of electric field is given by, or any charge is enclosed by closed surface, then we say that this is our Gauss law. Whenever this charge is positive, then this flux is positive. Charge is negative, flux is negative. Zero charge, no flux, or when we have dipole, equal and opposite charges. So then outward flux is equal to inward flux. So convergence भी है इलेक्ट्रिक फील्ड का और डाइवर्जेंस भी, और ये बैलेंस कर रहे हैं, इक्वल चार्जेस हैं, डाइपोल है, इक्वल एंड ऑपोजिट चार्जेस. So net is what it is, zero. So this is example of zero divergence here. Then you can check if we put sawdust or pine needles on the surface of water. Okay, तो जो velocity है water current का on the surface of water, you can see that vector, that velocity vector is a converging type of field, or diverging. What will be divergence of that? Then you can see how these needles, they sprint, they diverge out, or they converge, or they circulate. So that will give you idea about the vector velocity field. Then we have third operation. It is operation of del operator on vector field, and this operation is called curl of a vector field, and I put cross here between del operator and my vector field, and then I read it as curl of A. This is curl in short. I write CURL, curl A, curl of A. Mathematically, again, to find cross product, this is vector operator having components. You know what are components of this vector operator. You write components for A, then determinant decides what is curl of or cross product of two vectors. In I cap, j cap, these are directions, components, and components of del operator, curly by curly x, curly by curly y, and curly by curly z, and components of A vector field, ax, ay, and az, and then you solve this determinant, and you can write what you can write. A new vector, that is curl of A, having components in the direction of I cap, j cap, and k cap. So quickly, if you do, this is I cap, and component, this is curly by curly y of az minus curly by curly z of ay. This is first component. Then I write minus j cap. This is curly by curly x az minus curly by curly z ax, and third component is k cap, which is curly by curly x ay minus curly by curly y ax. So this is a vector quantity having three components in three different directions. You can find magnitude of this by squaring and adding all these and taking under root. That will give you magnitude of curl of A. And this significance is what? It gives you circulation. It represents rotation in vector. If I say that curl of any field, let me say electric field is 0. So this means there is no circulation, there is no rotation. Field is lamellar, represented by parallel lines of parallel vectors of same magnitude. One thing I forgot, that is divergence of, if divergence of any field is 0, then that field is called solenoidal field. Okay, field is called solenoidal field. As a field, this is solenoidal field. outward, inward, and net flux is what it is, 0. Flux is 0. This is flux is 0. So flux is 0, then field is what it is, solenoidal field. And solenoidal means that है ना, कोई भी हम यहाँ ड्रॉ करेंगे कोई एक वॉल्यूम और एक है ना, so you will see that this is what this is, net divergence is what it is, 0. And here, if curl of any field is 0, then that field is what it is, lamellar field, represented by, we'll see this in more detail. So this is whirlpool region on surface of water, and you can see velocity vector में क्या है, यहाँ circulation है ना. So you can see that if I try to draw velocity here, so you can see velocity vector here at this point, it is in this direction. So these are velocity vectors, and there is rotation, circulation. As I यहाँ बहुत ज़्यादा circulation, rotation है, but as I move away, so you can see that this reduces. So this is best example of velocity vector. Here is giving curl of this velocity vector is what it is, non-zero. There is rotation. Curl of velocity vector is non-zero means it is a rotation. Sorry, it is rotation. Rotation is there. Rotational field. It is representing rotational field. So these are the components of curl of any field. Geometrical interpretation, I explained, it measures circulation, it measures rotation in the field. ठीक है, so जितना field में circulation होगा, rotation होगा, more will be the curl. If there is no circulation, no rotation, that means curl of that field is 0, and that field is called lamellar field. Okay, so let us take example. This is picture showing what the field, this is field, and you can see what you can see. If you see these vectors or these arrows closely, so there is circulation in this field, and this field is is represented by this vector, which is minus y I cap plus x j cap. Okay, because it is in this plane, xy plane, so it is having two components only. This z, this is what this is, perpendicular plane, z plane. Okay, and then we have another field. This is represented by this, and I have another field here. You can see this is again in xy plane, and it is parallel to this axis. But if I move along x direction, you can see that magnitude of these field vectors, magnitude is increasing. Length of these field vectors is increasing as I move along this x direction. So you can see that this is represented, this velocity is represented x times j cap. Okay, so we can find, this is again one more exercise for you. You can find curl, because you can, by simply looking at this, you can see that yes, there is some curl. It is like this whirlpool. It is what? There is circulation. Rotation is there. So curl of this vector, mathematically, if you do, curl of this vector should be non-zero. Curl of this is also non-zero. This is also showing circulation. And you see this mathematically. Okay. Then this is all about what this is all about. Then we have two more things, that is two theorems which we'll be using while doing electrodynamics or electromagnetism, and those two are, first is Gauss divergence theorem, and another theorem is Stokes theorem. This Gauss divergence theorem is to have relation between surface integral and volume integral. वो integrals अभी हमने लिखे नहीं हैं, so I'll write first for you volume integral and surface integral, and then I'll write for you line integral and relation between line integral and surface integral. So these relations, because these relations are important to when we'll be doing Maxwell equations, we'll be writing wave equation for electromagnetic wave, and we'll be studying electromagnetic wave in different like conducting medium, in free space, in other media. So it will be useful. These theorems will be useful there. So if I simply write here, because mathematical description is not required, so curl, so this is a surface integral, closed surface integral of, let me write journal expression, not write E, let me write A vector, any vector field. So it is A field. So it is surface integral, or particularly, I must say this is what this is, closed surface integral. I have put this circle here. This is closed surface integral of A field. Okay, now we are operating with new operator, that is integral operator. चलिए वो उस डिटेल में हम नहीं जाएंगे. We'll simply say that this is what this is. You understand this is surface integral. If I put here this, then it is what it is, closed surface integral of A. And closed surface integral of any vector is related to volume integral of divergence of that vector by this relation, divergence of A. Okay, so this is a relation between what? This is a relation between surface and volume integrals, and through this divergence. So vector field हमारे पास है, and if I have surface integral of that or closed surface integral of that vector, so that is equal to volume integral, or you can say volume integral of divergence of that vector. This is Gauss divergence theorem, and we have divergence, DIV, I am writing in short, DIV theorem. And then we have one more theorem, that is Stokes theorem. In mathematics, you have even proofs of these theorems, and you have तो उतना detail हमें नहीं चाहिए. I mean, in short, we want. So, line integral, closed line integral of any vector field is related to surface integral of curl of that vector field. So it is curl of A surface integral of this. Okay, so these relations you should know so that we can do. So this is all about, this much mathematics is required. Okay, we have done 3 operations of that operator: gradient of a scalar, divergence of vector field, and curl of a vector field. And then we have 2 theorems, Gauss divergence theorem and Stokes theorem, with physical significance of all the operations of del operator, and with the mathematical technique how we operate with these with this del operator on different fields. So this much knowledge, this much idea will help us in doing this chapter in more detail. So with this, if you have anything to ask, any queries, you can ask. And if you do not have anything to ask, then you can hang up. I will upload that assignment, as I said, on Google Classroom by today evening.
Thank you, sir.
Okay, beta.
Thank you.
Okay,
Thank you, sir.
welcome.
Thank you, sir.
Welcome.